Consider the following problem. We have a continuous function f from the real numbers to themselves. F is periodic with period t. So for any real number x, we have the f of x plus t is equal to f of x. And we'll define a new function, capital F, evaluated at x, given by the definite integral from 0 to x of f of t with respect to t. We want to show that we can represent capital F of x as a sum of a capital G of x plus mx. M will be a real number. G of x will be a periodic function on the real line that's also differentiable. Now, before we do any work, let's take a look at an example to see what we should expect. So, if I want to consider, say, a nice periodic function on the real line, let's consider f of x equal to 1 plus sine of x. So here the period is going to be equal to 2 pi. I use 1 plus sine of x because I want the area under any region beneath our graph to be a positive area. So I don't want this to go to below the x-axis. Now, if we consider capital F of x, well, what do? We're going to take this definite integral. That'll give us 1 plus x minus cosine of x. And we'll note this is going to split into two pieces. We'll have a periodic function given by 1 minus cosine of x. Then we'll have the mx part given by this term where m is equal to 1. Now, the question is, in general, why should I expect to be able to split a line off of capital F of x? So let's think about what our graph of capital F of x looks like. In general, what we're doing is we're just taking the net area under our function little f between 0 and x. Now, what's going to happen at, say, 0, 2 pi, 4 pi, 6 pi? So I'm only going to worry about points where we travel out by one period. Well, as I go from 0 to 2 pi, we're going to have the area underneath one period of our graph. If I go to 4 pi, since our function is periodic, we're going to be taking the area under two periods or twice the area under that first period. In general, if we evaluate capital F at n times the period, we're just going to have n times the area under that first period. So if we plot those points, we're going to have a line that has slope. Okay, it's going to be given by the area divided by the period. For general f, capital F of 0 is 0. Capital F at t is equal to a, the net area under one period, say from 0 to t. And then capital F on an integral multiple of t is just that integral multiple times a. So when n is positive, all we're doing is taking that first period and then we add it to itself n times. When n is negative, it's still consistent because if we go to the definition using the integral, we're going to switch the order of the limits and that'll introduce a minus sign. Now, in general, we're not going to have an increasing function for capital F. So it'll be increasing if little f is greater than or equal to 0, which we had in our example. But in general, it's going to move back and forth, but it's going to follow a straight line. Okay, and from the information we have here, the slope of this line is just going to be given by, okay, we take a look at what happens between any 2 points that we've looked at. So I could take, say, the point NA and 0, 0. We'll have slope A over T. Now, that suggests that we take capital F and subtract that line off. So that line's going to be A over T times X. So this is going to be my candidate for G of X. Now, before we do the proof, I want to note one fact. So, in the general case, okay, the area, say from 0 to t underneath of our graph, that I could find by taking any period starting at the real point x, going out to x plus t. So the easy way to see this is just to draw the picture. So here I'll have our region going from 0 to t. Okay, it doesn't need to be above the x-axis. We're just going to take net area. If I go from x to x plus t, note I could chop things off at t, and then I'll just take this piece, move it over to here, and we have the same area. Okay, and this is going to work no matter how far out our region is. Let's show our result. So recall, we're defining g of x this way. Capital F of x is being defined by this definite integral. And we want to show that g of x is differentiable and that g of x is periodic with period t. So g of x plus t is equal to g of x. For the first part, we invoke the second fundamental theorem of calculus. So recall what that says. If we define our function capital F in this manner, okay, here we'll have little f continuous everywhere, then the derivative of capital F, I'm just going to take the integrand and replace t with x. So the derivative of g is just going to be given by little f of x minus a over t. So not only is our function g differentiable, it's continuously differentiable. That's part one. For part two, okay, I want to show that g of x plus t is equal to g of x. So I'm just going to follow my nose with the definition of g. So what we're going to get, we're going to have capital F of x plus t minus a over t times x plus t. Okay, so we'll multiply this part out. Then I'll write out the definition of capital F. Now, from the previous board, okay, if I have this area, we could take it over any period. So I take the period going from x to x plus t. Now, we have rules for addition of integrals. So what will happen here is these two integrals I can combine to give an integral that goes from 0 to x. That's going to mean that we have f of x here, and then here we just have the minus a over tx, which is just going to be the definition of g of x. So that gives us our second part. So that's our result.